Okay, I'm going to hit interfaces and collections. The interface concept I didn't actually ask you to implement in any of the assignments. Collections we are implementing, and so, but it's not bad. In fact, I know I said I wasn't going to do PowerPoint, but some of the concepts are easier explained via PowerPoint. So I'm going to show you quickly, going to go through some PowerPoint stuff, and give you some definitions of different things so that you know what I'm talking about in terms of the theory, in case this is brand new to you. Then I'll show you how it's implemented and go through assignment number 2 and assignment number, no, excuse me, 3, and actually assignment number 3 is the one I'm going to go through for collections. Assignment number 4 has to do with the GUI stuff, and so we'll have a break, then we'll come back and we'll do GUI. So break it up a little bit. So what do I mean by interface? So an interface is a way of describing what a class should do. It's not like an abstract class. Abstract classes are inherited. One abstract class we saw in the person. We inherited a instructor. We inherited an employee from that. Interface is done a little bit differently for a different purpose. So without specifying how you should do it, it's not a class, but it's an interface. It's defined as an interface. So basically you're telling classes what the requirements are going to be for the class that you're going to build from. And it is only an inheritance concept. You don't build interfaces unless you're working with inheritance. So you want it to conform to a particular interface, and here we have a public interface comparable where we have a method in here compared to take an object and compare it to another object. So it requires that the class implementing the comparable interface contain a compare to method, and that the method must take an object parameter and return an integer value, because we have it set up the method as an integer. We actually saw this. We saw it in our abstract class, and this was the string to string method that we declared as abstract. So it's similar but a little different than abstraction, which is why it's kind of like, if you know the concept of an abstract class, interfaces make sense usually. So the declaration consists of the keyword interface versus abstract, and along with the name and the members that are associated with it. Similar to classes, interfaces can have 3 types of members. They can be fields, data members, nested classes, or nested interfaces. You could put a class inside of a class, actually. We haven't really seen very much of that. And here's an example here down here where it says interface verbose has got silent, terse, normal, and verbose. We have different settings for integer values that are associated with it. So let's define a constant. So we can say public, static, or final. The modifiers are omitted by convention because it's not really a class template, it's an interface. So we're going to build a class from this. So in theory, we can leave out the access modifiers. It doesn't really matter because none of the functionality is actually runnable. And the names of the constants must be initialized. If we're going to have a constant variable, if we don't initialize it, it's worthless. We can't use it outside of the interface anyway. So they're implicitly abstract, but we omit the abstract word. So we never say abstract interface. It's kind of an assumption. And in some ways, the interface and the word abstract kind of go hand in hand. There's a lot of similarities between the two. And they're also implicitly public, so we can admit that as well. So in here, we just saw interface verbose. We didn't see public. We didn't see abstract. Nothing of that nature. And they can be final nor static, so they can't be either one. Because you're not really using anything outside of the interface. You're using it for inheritance reasons. You're implementing it. So the modifiers for the interface itself can be public or abstract. And to implement the interface in a class, this is really the important part to see how this is used. And you're not going to be asked to create an interface for any of the assignments for this class. And it's a nice concept to know, however, for the final. And in fact, I don't even think I asked you anything about interfaces. Maybe there's one question on the midterm, I'm not sure. But it's really a concept that you use when you need to. You're not going to necessarily use it for everything. And towards the end of the slide set, I'll give you some examples on when you'd want to use it. So you have 2 steps to make a class implement an interface. Declare the class intends to implement, and given the interface by using the implements keyword. So we have, in the other example, when we extended, we used extends for inheritance. Now we have implements. So you can extend a class and you can implement an interface all at the same time. The trick is you can implement more than one interface. You only extend one class. So sometimes people will say, well, this looks like multiple inheritance. It is kind of like multiple inheritance. You can follow multiple interfaces instead of extending one class to another. Because so far we've seen this class extends, this class extends, this class extends, this class. Now we can take a bunch of interfaces and implement them in one class. So that's why we use interfaces, long story short. Otherwise they wouldn't really have a place, they wouldn't exist. They're not really abstract classes. Because if we called them an abstract class, we wouldn't be able to implement multiple ones of them. So we're, again, enforcing rules at a higher level for inheritance so that we can implement certain, and here's the example on the bottom. So a single class can implement multiple interfaces, just separate them out by commas. So class employee implements comparable, comma, clonable, comma, whatever, comma, until we have included all of the implements that we're interested in doing. If the class leaves any method of the interface undefined, the class becomes abstract class and must be declared as abstract. So we have to define the methods. Where abstract, we just list them. So we can turn an interface into an abstract class by our style of programming by omitting information. Long story short. So instantiation properties of the interface. Interfaces are not classes. Abstract classes are classes. They're called interfaces, the interface. So we can never say new operator to make an instance of an interface. Doesn't happen. So that would be illegal. We can still declare interface variables. We can say comparable X, and comparable is an interface, not a class. We can actually, and this is a variable that's representing that interface. So you have to refer to the object of the class that implements the interface. So if class employee implements comparable, X is equal to new employee. Well, it's also an interface. As we've seen before with inheritance, we have the interface, we have the object, every object that came before it, all the way up to object, actually. And we can actually treat objects as objects as well. We can just call object. Because every employee, every person is an object, if you think about it. We can extend interfaces. So here's our multiple inheritance. Interface supports multiple inheritance, and interface can extend more than one interface. So superinterfaces, subinterfaces, they can exist. So we have the same concept of inheritance. So public interface, serializable running extends, Java.io serializable, runnable, a bunch of other stuff. So it exists for flexibility, essentially, and to give us multiple inheritance. This is why. But I'm not going to trouble you with an assignment that uses an interface. What's going to end up happening is you're going to be working on a Java project, and you'll say, interface, what is that? Oh, it looks like a class. It looks like an abstract class. It's not, though. It's just defined as an interface. And then you say, implements this interface, implements that interface. Oh, what is this? All these interfaces. That's how we combine different behaviors, different functionality, and we put it all into one. So you could rewrite the whole thing, put it all into one class, maybe. Here's a tedious example in terms of the details. So when the interface inherits two or more constants with the same name, you can basically specify or reference the interface. So here we have, it is a subinterface, explicitly use the subinterface name that's referred to it. So you're doing here a.value, b.value to say this is from the A interface, this is from the B interface. Here we have interface A, interface B. We actually kind of do interfaces, so let's say you're doing like a math or accounting program. You could set a bunch of constants, a bunch of calculations, and use the interface to say, hey, I need pi. Okay, here's pi. And you just use it because implements the uses the interface. Okay, good. So we just use pi. We just use the stuff out of there, which makes it a little bit easier. And if the superinterface and the subinterface contain two constants with the same name, then one belonging to the super interface is hidden, and we just have the subinterface. Because super is above, sub is below. Yeah?
Is it extends or implements?
It is, it is implements. We extend classes, we implement interfaces.
Next one.
Oh, is there a typo on the slide? Interface. No, it's actually extending classes. The example is extremely confusing, which is why I actually don't even like this slide set. It is the proper terminology is implement. So employee implements comparable, which you'll see extends a class is to inherit it, implements it is to use the interface. And so to extend, we're specifically inheriting, creating a subclass. When we implement, we're not really creating a subclass because the interface isn't a class. It's just an interface. C++, what do they call them? Templates? I can't remember. No, templates are different. But
they also got interfaces.
are templates interfaces? Yeah.
And,
Template classes? Yeah.
And interfaces.
Oh, they also have interfaces. Yeah. I was one that left C++, and the memories are fading. I don't like C++. I hate the language. Java's so, and you're going to see in the next lecture, Java's a piece of cake.
I also hate it.
You hate C++? Oh, good, we're on the same side.
C++ people hate me when I started.
C++ hate Java people because they don't think we haven't gone through the trenches. We haven't worked as hard as they have worked.
Sleeves and do everything like delete everything.
Yeah.
But Java doesn't.
Java people, everything's done for you. But the thing is, why use a manual row push monower when you can get one of the gas-powered electric ones and turn it on, go get the grass mowed in a half hour instead of all day? That's C++ and Java right there. Mowing the lawn. Of course, it's raining outside, which means we're going to have more grass to mow, which means you better get an electric mower. Learn Java. All right, so extending interfaces. What about the methods? Well, you can override. So overriding an interface has no question of ambiguity. The real behavior is ultimately decided by the implementation of the class. So it's not like an abstract class. It's like a template. I hate to use that word, though. All right, why use interfaces? Here we go. We have interface shape. Class implements this interface point. In fact, this example for you is out on the website. It's in the lecture directory. Under below it says lecture examples. This entire program is out there, so you can compile it, take a look at it. The usefulness of the interface goes far beyond the simplicity of publishing protocols for the programmers, which is what you're using an abstract class for. You're basically telling them, you need to have this two-string function. You need to have that. So any function can have parameters that are of an interface type. And an object of the class that implements an interface may be passed as an argument. So, clonable, clone. All right, let's talk about clonable for a second. So the marker tagging interface has either methods, they don't have methods or constants. So the only purpose is to create an instance of in terms of the type inquiry. In fact, we've seen the instance of in that example for assignment number 2. We have the clonable interface as an example. So one clone is a clone method, returns a new object whose initial state of the copy is a copy of the original object. So we can actually clone objects so that we can make different instance of type checks to them and treat them as different objects for compatibility purposes. So 3 factors are involved with cloning a method. So the empty clonable interface must implement it to provide a clone method. The clone method implemented by the object class performs a single clone of copying all fields. So clone not supported exception will occur if the functionality won't work. So, and I forgot to tell you, we kind of transitioned. This was the last slide of the interfaces. I'm talking about a clonable concept at this point, which I don't even believe. No, I did cover this actually. The clonable is basically an object class providing the method clone, which performs a simple clone copying. We can actually do shallow and deep cloning in terms of objects because we have objects that can contain other objects. And it's just like C++ actually, shallow and deep copying, when we can take a piece of a variable, we can take some information and just make a shallow copy, which is a assignment almost. This variable equals this variable kind of copying. Or the deep copying, which takes this object and all of the other objects that it contains. It physically copies the memory that's associated with all of the contents of that object, makes another equivalent object to it. It's a standalone existent object versus a copy of the first object. So that concept actually exists. It's going to not really use. In fact, I'm going to skip through that because what I really wanted to cover out of that lecture was the interface design. So I know that was kind of quick. That was everything you ever wanted to know about interfaces without the boredom. And the simple thing is that there's nothing really with an interface outside of it. It's just like an abstract class, but it's not a class. It's an interface. And you can implement multiple interfaces in one class. And if you follow along with the inheritance stuff, you're just implementing behaviors and using methods that exist. So it really does, interfaces really does support the concept of reuse in terms of the object-oriented design. The next concept and the theme of the assignment number 3, which I'm going to go over momentarily. I'm not going to go over this entire slide set. I'm just going to give you the concept of collections, because that is better said with a picture in words. What is a collection? So this is where the C++ people are pulling out their their manual lawnmowers, or they're out there with a pair of scissors, and they're cutting the grass with a pair of scissors instead of using a lawnmower at all. Because if you have ever experienced lists, linked lists, queues, stacks, all of these famous data structures in C++, you probably quit and got into something else because it's a nightmare. In C++, you have to create a linked list if you want a dynamic array, because we don't have a dynamic array, an array list. We just have an array. So we have an array. We have the built-in data types of an array. We've seen the array. Hopefully you understand the concept of it if you're brand new. Look at the front row here. So a dynamic array is one that can grow unlimitedly without having a limit of 10, a limit of 9. A static array, the regular old array, is static. You assign it a value. Once you initialize it, once you declare the variable, give it a size, it stays for the entire program. Not so useful. So C++ programmers have created linked lists. Linked lists is using pointers normally to allocate dynamic memory to create an array, essentially a list. And the way the linked list works is we have normally a list as a structure that you actually have to create, sometimes using a class, very popular. You can actually create one using structures. And inside of the class that you've created as a list, you've got nodes, a subclass that represents each one of the items in the list. And it's called the linked list because the first item has a pointer, pointers. It's pointing to a memory address of the second item. It's pointing to the memory address of the third item, to the fourth item. So we have an ability to use what's called a collection, which is the theme of this particular lecture and concept, and also the theme of your next assignment, that deals with organizing these components in here, either as a list or as a grouping, as a bag, so they call it, or as an ordered, unordered, as a collection of items. Java's easy. It's all built for us, and it's in the Java.util package. So we already have a linked list. We have all of these things here in the picture on the bottom of the page. We don't have to implement anything manually. And I'm going to show you with a lot of examples in a few minutes how easy it is compared to C++. So the collection, by definition, is a data structure. If you're not a traditional computer science student, you didn't get this as an undergrad, but normally you have to take a data structures class as an undergrad. It's not even a math class. It's a programming class with data. I mean, it's interesting. Actually, an object, we grade as a class normally to represent the object of a tree or the object of a node on the tree or an item or linked list item. Check out Java.util package. Lots of interfaces and classes that provide a general collection framework. This concept actually works with the interface, and so you'll see it in the next assignment. Next assignment is going to look a lot harder than it really is, actually. Did you guys find number 3 hard? Did you do number 3? The hash map, a hash table,
multi-map.
Multi-map. Was that hard?
Yeah.
Yeah? All right. I'm not going to do the assignment for you. It was hard compared to number 2?
Yeah, it took a few hours access.
A few hours. That's not too bad. As long as it takes more than an hour, less than 5 hours.
Yeah, somewhere around 3 hours.
About 3 hours. Okay, that's doable. Well, I'm going to show you some examples, so it might make your job easier. In fact, it'll make part 2 easier. I'm going to do part 2 for you. I'll leave you with part 1, and I'll show you that in a few minutes. Some of you are looking at me going, what are you talking about? All right. So let's see. Again, what time did I say? 1:15, something like that. What time did I say I was going to break?
That's what you said.
Okay, good. Okay, I'm just keeping track here. I'm pacing myself. All right. Because what I really want to do is show you the examples, but I got to give you the concepts first. All right, so check out the Java.util package. That's what we're using. We're importing that. We're going to use linked lists, ArrayLists, everything already for us. So we don't have to reinvent the wheel. We don't have to create these on our own. What do we get? An overview of the interface, and I'm going to show you an example of all three of these. What do we have? We have the concept of the collection, and this is the terminology for you. This is the concepts. The collection is the list, is the set. The differences with the list is we have the array list and we have the linked list. It depends on how we're going to use the list, whether we want an ordered, whether we want just a compiled list, whether we want to sort the list, how we're going to use the list. In terms of the set, we have a hash set, and we have sorted sets. And I'll show you an example of what I'm talking about with that. And then we have the map concept, which is what your, with a key and a value, which is what that assignment number 3 is. The first part of it is referring to. And then we have this concept of an iterator. And then we have this comparable object as well that we can use as a class, that we can actually create and make a list comparable, and that way we can actually manipulate the items of the list. And the iterator is going to go through, it's kind of like what the C++ people do with the for loops. In fact, we've seen iteration in that last example where we've gone through each one of the objects, checked to see if it was a student, checked to see if it was an instructor, kind of spent a lot of time iterating and over again. So that's basically, we have an iterator class that gives us, print out in reverse order, print it out in forward order, split it in half, do this, do that. Just tell it what to do. And some root interfaces for the collection is what we're looking at is something to get the size, is it empty, what does it contain, add an item to it, remove an item to it, and contain all, add all, remove all, retain all. So the iterator concept, we're looking at the collection interface, and it defines what's called in fact, these 3 categories have interfaces for the collection concept that it's implemented. And in terms of what the iterator is doing is it's doing our sorts, or it's doing our, does it have a next, does it remove, and it makes no sense to look at this on a slide set, so let's actually, at this point, I've gone through the definitions. Let's take a look and actually see what it looks like. So we are on assignment number 3 now, and actually, let's take a look at the monster, see what we have to accomplish here. I did not put together anything for number 5 because I ran out of time. So number 5, you're going to have to watch the video on, and maybe I'll remember to send an email message out to point you to it. But I'll solve 3 and 4 for you. Okay, assignment number 3 extends hash map. That's a file that's given for you. So when you go to download the assignment, you're going to see 5 or 6 different supporting files. And you're going to, in fact, I'm going to upload links to the videos that I'm recording that's going to show you. So just in case you haven't written everything down, you could cheat. You could pause the video and write the code down. But hopefully you're going to do it yourself. I'm not going to give you the source code for it. However, here we do give you source code files. And what you're going to do is you're going to edit a file called multi-hashmap and .java. You're going to add new methods and override 2 methods from hashmap, because multi-hashmap is extending hashmap that's using interfaces for the collection for the map. So you need to implement some 4 new methods. See the file, you're going to get all, put all, contains, and remove. It's, I wouldn't say difficult, it's taxing because you have to figure out the logic. And the logic is like, if you're familiar with C++ and if you've ever built a linked list, there's your problem. How do we reassign? You don't have to worry about reassigning pointers, but you do have to worry about the logic of how do you remove all the items. Well, removing all the items is easy. How do you remove just one item? How do you remove, how do you figure out what the object contains or what's in the list? So the functionality is not trivial. That's the hard part of it. The overall, not like assignment number 2 where you actually have to know about object-oriented concepts to understand that. This one is different. This one's more like, can I figure out the logic of a remove all? So I can still retain the list structure, but I'm just removing the items, stuff like that. So, and this works with the overriding method, so you have to override 2 methods. And when it says the same signature, that means it has the same number of parameters, the same template. So the get and the put. The external behavior of the get and the put is the same as the hash map, but internally they should facilitate the ability to keep track of multiple associations, stuff like that. So you can read through, and essentially what you're doing is you're working with a collection, and it's going to be a map collection. And you actually have to, and I'm not going to spend the time to go through each one of the different files. What I want to do is kind of give you the second part of this. Here's some sample, here's some pairs, some logic. All right. So hint, multiple objects can be organized inside of a single object. Yeah, so with that concept in mind, it's kind of like the linked list of the C++ days. And the iterators cannot guarantee the order of the objects returned from the collection. If it's an unordered collection, it's just a set. So consider how to reverse the order of the objects associated with a key. Kind of tricky. And on this particular assignment, if you don't get all of the functionality, this is your bonus for showing up today and listening to me or watching the video. If you're at home watching this video, looking for as much implementation as you can do. If you get more than half of it in there, you're going to get full credit. I'm not going to nitpick. And the TAs, whoever reviews this, which is probably going to end up being me, not going to nitpick on this one. Because this one, you could get it sort of working but not working. You can get part of it but not all of it on this first part. And you could get it and it could have errors in it. What you want to do is make a reasonable attempt to get this one. The second one is kind of straightforward. You probably should, the second assignment, you could probably do that one completely. And that one we are going to kind of run and see if it works. But this one here is slight freedom of oops, and I scrolled down to the second part. Slight freedom of interpretation and winging it, or improvising, I should say, or however you want to word it. So you don't have to be right on with everything, that's what I'm saying. You could be sloppy with that one. The second part is actually kind of easy. There's 2 parts. There's exercise 1 and exercise 2. And exercise 2 is what I'm going to give away. I'm going to show it to you. Exercise 1 I'm going to let you play with and figure out on your own. So we have the class Java.util is that collection. Don't confuse this with the collection, single one. Provides useful static methods for collections, lists, sets, such as sort and binary search and all sorts of different things. So in this exercise, you're going to utilize the collections.sort method on a list of your own, abstract data and type. So you create your own abstract data type, you create your own list. Normally, we have the sort list. It takes the argument of the list of comparable elements. We'll see an example of that. Modifies the list so that the elements are sorted. And then if you wish to do a sort on it, you can do a sort on a sorted list. So we wish to sort a collection using rat number objects, but rat number does not implement the comparable interface. So we can't use collections.sort, I should say. We'll see. I'm going to show you how that's used. So you can kind of, right now you're probably going, what does she mean by that? So you can simply modify it, but assume that the option is not available, and actually gave you the file. So the file you don't actually modify. I've actually had some students ask me questions about this already from the weekday class. It's just given to you. You can look at it, read it, look at it. You don't have to use it. In fact, you're not supposed to use it. You're supposed to write your own class. So the functionality is given to you. You're just going to implement the collections.sort, and you have to implement a comparable element to do that. And I'm going to show you how to do that. So you'll see how that's done, along with some other examples. So now the comparable, and this is just going through what the comparable is doing. It's a class that you're implementing, and only need a single method to compare one object to another, so that you can sort the list. And it's dealing with sorting. So now with comparator defined inside of it, you can simply return 0 after you run the compare method to compare one object to another. So I know it makes absolutely no sense. Let's take a look at it. So what do we got? I put together 1, 2, 3, 4 examples. I'm going to make this bigger as soon as I open it up. Let's take a look at the list example. And make this bigger. There we go. Ooh, that's really big. And here, actually, I kind of discovered something interesting. Because it's storing objects, the objects can actually be, for this purposes of any data type, can mix and match, actually. Which is kind of a weird side effect that I just noticed. But the capability is there, but I'm not even demonstrating that. The key part here is you need to import Java.util. So add that along with any of the other imports that you're using. The functionality we're implementing comes out of util. This particular class is called ListExample. And this here is suppressing warning messages to make my interface look better. And the warning messages is because I actually haven't specified data types here. I'm creating a list, and here is how most of the C++ people are going to fall over in their chairs, because they're going to be, what? How easy is this? This is extremely easy. What is that? That's an array list already created for you. So the class already exists. And it's in the Java.util functionality. So list equals new array list. Where'd that come from? Standard libraries. Old days we had to create an array list. Yeah, not so good. List.add 1, 2, 3. Oops, I changed this. This should be 2. 2, 2, 3. I put strings in here. I'm kind of cheating because I haven't actually specified the data type. You could specify a data type and call them strings, which is actually what I put in there. And then now I'm going to say my list equals my list, right? And this is an array list. We all remember arrays, right? But the regular arrays are fixed, 1 through 10, 1 through 11, however we define them. We have our index values 0 through 10. Now we have one that's growable. Why create a standard array? In fact, we could make the students, unlimited number of students. We can have a class of 350 students for one instructor. Or one that has 10 students in it. Which is why people like this. Which is, you're not familiar with it unless you're looking at the Java utils, actually. So we create the list, and I'm going to just print out the raw list here. And then now I'm going to say get item 2, get item 0. Running methods on the list to get. So I can put get, I can manipulate the list with built-in methods. And link list down here. Oops, actually, now that I put that suppress warning, I can actually take this off. Well, actually, you know what, let me leave this on here for a second, because then I can show you. Let's say if I wanted to explicitly say what data type I'm going to use. I've explicitly stated string here. Linked list is going to hold strings. And I'm going to create a queue. And it's going to be a new linked list string. If I wanted to, because I suppressed the warnings and I don't want to specify the type, I could go like this, actually. And because I have this up here. And this is part of the Eclipse. If you leave out the type, Eclipse is going to... Actually, here, if we take this away... cut. Let's see what happens. We get this stuff. These are warnings that show up. I don't like it because it makes it look, it messes up my interface. It messes up the picture, right? So if I kind of, clicked on the warning or show it as a linked list is a raw type. Yeah, I know. Reference to a generic type linked list. You should specify a data type that you're going to use in this linked list. All right. So I can add a suppress, add the warning to suppress it so the little yellow stuff goes away, or infer a generic type of the argument. If I infer a generic type, then it's going to ask me, do I assume it for everything? Yes, I do. I just click it. Then it's going to automatically stick the string in there for me. And it automatically put in here string on my list. And now I don't have the warning anymore because I specifically stated the type. If you're not using Eclipse, you're doing this out in Java, it'll compile just fine. You're not going to get the warning. This is an Eclipse thing. It's a warning to, you should not have typeless variables, but they're objects. And the object is of an array list. So it's an instance of an object that you're creating that doesn't necessarily need a type, if you think about it. Because what I can do here, actually, and this is the interesting part, I wasn't even thinking about. I've now mixed because I'm treating them like objects, I've got, oops, no, actually because I have string here, hold on. Let me get rid of the type. Actually, I haven't, no, let's not save it. Open it back up again. Now I have the warning in there. Let's just do this. Now I've mixed and matched types. Except for my typing isn't so good. Let's see. 3. Let's call this 2. I don't know why. I don't know how. I was playing around with the example. Not too kosher, but let's see if it works. So now in here we're going to print out, let's say, the items, and this is going to print out get 2. So 0, 1, 2 is going to print out 3. Actually, here it's 0. Let's put here 0, 1, 2. Actually, let's put in here 0 so we can see it. 0, 1, 2, 3. Or okay, for those, I was going to say for those obsessive compulsive. Yes, that's me. Okay, so now my list is ordered correctly, except for I've got that 2 in there that's bothering me still, but I'm going to leave it alone because I'm demonstrating a point that's being treated as an object. If I try to write a method to overwrite this at, I'm going to have a problem because I need to know whether or not that parameter is a string, an object. You know, what is that? So I'm getting away with it because I'm suppressing those warnings. I'm not paying attention to it. And so anyway, I'm just printing out, I'm getting item number 2, I'm getting item number 0. And then here I've created a linked list, and the link, I'll just leave the string in there. We've got add first, add first, add first. I could say add to the last, add to the first, add to the last. So now and then you're thinking, well, what in the world is a linked list? We know what an array list is, right? It's a regular old array, but it's created as a list. It's growable, and we can store generally items of like type in there, and we can actually make it grow. And it's a dynamic array. Sometimes they call it a dynamic array. Sometimes they call it an array list in C++. Usually it's created with pointers, and it's created by the programmer in C++. Java, no. The linked list is another structure in which we've got lists, and that can be created sort of like a queue or a stack. And the way, you guys know what queues and stacks are? See, some of you guys are like experienced C++ people, some of you are just learning Java. Stack, the way you remember it, you'll never forget it. You open up the cabinet, you put the plates from the dishwasher into the cabinet, and you stack them up. 1 plate, 2 plate, 3 plate, 4 plate. When you pull the plates off, nobody ever pulls all the plates up. Picks one off the bottom, will break everything. So you pick the plate off at the top.
Is it first in, last out?
First in, last out. But if I say first in, last out, maybe stack, always remember stack of plates. Queue, remember every time you wait in line to the bank. Bank is a queue. Lines are queues. First in, first out, because that person's waited longer, right? So here we have got the logic where we're adding to the first. Why do we have to always add to the back? We can create a queue, add it to the first. Now you're the first person. Oh no, now you're the first person. Now you're the second person. Oh, now you're the first, second, third. First, second, third, fourth. So we keep adding to the front of the line, which is great because in these data structures we add to the front, add to the back, add to the middle, add it anywhere we want, create any type of structure we want. This functionality is already built in. We don't have to. This is a nightmare for C++ people because you have to do this with pointers. And you have this concept of next, previous. We still have next and previous, but it's already built in for us. So we're going to create a queue, my queue. We're going to remove from the last, because we got a first in, last out. No, first in, first out. First is our stack. And the last 2 have been removed, and here's the contents of the queue. When we print the queue out, we just go queue. We're not the structure, so let's see what this sucker looks like. I think I might have to save it. I'll just save it anyway, because I think I made some changes to it. We'll run as a Java program. Oops. Here we go, and you see we have no error message at all, and I got it mixed because I didn't put types on it. I used raw. So we have 0, 1, 2, 3, 4. Item number 2 is 2. Item number 0 is 0. And then we have a queue, 10, 9, 8. This is the reversed order because I added it to the front, added it to the front, added it to the front. And then after the last 2 removed, take 2 off the back, and we have 10, 9, and 8. 10, 9, or whatever. Right, so Hopefully you can understand the logic of that. That is about, I don't know, 2 or 3 hours of C++ work. 5 minutes in Java. Not bad. So now next time you implement a queue, implement a linked list. Can I do it in Java? Sure. All right, so that's a list. Those are list collections. Let's take a look at a set. That's where we get like a hash set. So the hash set comes already. So what's a set? We're just adding. We're not adding to the top, adding to the bottom. We're not keeping an order of the items like an ordered list. Because we have lists that might be unordered as well. We can create order out of it, and that's where we get the collection for the comparable. I'll see that in a few minutes. So here I have a set example, same library. We just include the same library for everything. We're going to add 1, 2, 3, 4, 5 to the set. We're going to print out the set, and then we're going to take this set and turn it into a sorted set. And it's going to be a new tree set. And it's not going to look, you're not going to understand what it looks like, but it's in a different data structure. So we've taken a set. Once we've got a set, we can send it as a basic set to another structure, create a tree out of it, create something else out of it. So we can take the collection and use it as a collection, just like we took the array of people and used that as a collection, but it was a regular old array, which makes it powerful because then you can take a whole set of stuff, take all the students and find out something about them, or sort them in an order, or do something with them. So if I run this, and I'm going through this a little faster because I'm assuming you guys got the basic concept. Oh, we don't need to save it. I say run as a Java application. Here we go. Now we have our set, our original set, and then we have our tree set. So apparently it built in a tree order for the structure in which we can perform tree operations, which might be traverse a node, move a node, and count how many things are in a node. And we're not really using it for anything, so we have no application to figure it out. But for sorting and sorting, if we can figure that out back from data structures. We have tree structure, abstract syntax trees for language processing, trees for all sorts of different applications that we might run into in terms of having to search. The classic GPS application sort of runs in a tree kind of format. Actually, that's kind of a slow implementation of an algorithm, but where we can map something out, find out, well, which is the shortest route from A to B, and then we can find, with freeways, without freeways, creating a tree structure essentially, and then traversing the tree to find out the distance, longest path kind of problem. So I can't teach you data structures in an entire semester along with object-oriented programming, along with Java. So if this is all foreign to you and you really want to get into software engineering, it would be beneficial to take a data structures course, which is why undergraduate students are normally having to do that. Let's look at the linked list example now. And each one of these examples is kind of building a little bit more. This one I purposely, instead of saying Java.util ***, I purposely said collections, comparators, and linked lists, because this is what was in the lecture. So you can kind of see how that lecture, and you can go back and take a look at that and compare, although it kind of reads like Greek and it's really hard to see it. Actually what you can do is just take this video and pause it after this weekend and you can get all this code. Here I'm taking and creating a class called linked list example, and here I'm using an integer as a data type. This is one way of doing it. You can actually kind of go through and create an integer linked list and then say the integer linked list is equal to a new linked list. You can do it another traditional kind of way as well. But here we are adding two, and then that's LL. It's the name of my linked list. Although it looks like programming language syntax or something. It's really a name. I guess I could have spelt it out. We're adding things to a linked list, and then we're coming up, and this is what the assignment's having you implement. Collections, because we want to do a sort. This is what the assignment is talking about. This is what you're implementing in that rat number, which is not using this. It's using a different technique. So this is an example of what it's doing, and it's creating a collection that's comparable, which means we can sort it. The linked list by tradition, is a piece of memory, linked to a piece of memory, That's how we learned it in C++. We dynamically created a new integer, and we found the memory address of that new integer, and we said, okay, good, now create another integer. Okay, make you the next. So we gave you the first guy's memory address, and we kept track of all of these pieces of memory by their memory address. And even the nodes themselves didn't know what their address was, but they knew who they were next to. So there's no order in that. So you had to create a, there's no really first or last. You can put them in anywhere you want. They're just memory addresses that are connected by pointers, but we don't have pointers. We just have memory addresses. So we just create a bunch of memory addresses, and we have, all of a sudden, they're linked together. And we can go through it, but we have to create an iterator to do that, to find the next, And so we just keep, just like the person turned into an instructor, but down the base they were a person. Well, here we have a linked list that's a linked list that ends up turning into a sorted collection, that ends up turning into a sorted collection with an iterator, that ends up turning into, we start adding functionality to it until we get what we want, which is why this assignment comes after the last one. You're supposed to know how to inherit. You're supposed to know how the objects work with other objects in order to kind of understand this one. All right, what are we doing here? We are taking, and we are sorting. What are we doing? We're shuffling. So we have the LL list here. And we're sorting the LL list as a collector item, as a collections item, and we're doing it in reverse order. So we're adding a comparator to it, which is an object that says, let's compare. So now we have the ability to get at the information that's inside of each one of the memory addresses that we're storing. We don't actually have to create the memory addresses. The structure is doing it for us. So we have R as the comparer, and we're applying it with a sort. This is essentially what the assignment's asking you to do. And we're just going to print it out to the screen. We're going to list out the sort in a reverse order, because we've got a reverse order method on the collection. And then we're going to print it out. We're going to shuffle, randomly shuffle things around. You just take all those memories and just shuffle them around randomly. And then print out the shuffle list. And then we're going to actually use the collection and find the minimum or the maximum. We could go find the size. We can find all sorts of different information depending upon the methods that we've written. And the good thing is, because this is Java, we can overload, extend, and overwrite behavior, customize it for our application, and then add new methods to it. What if we want to find the minimum that belongs to, the minimum that's not this value? Okay, so the minimum is no longer a negative number. The minimum has to be a positive number or something. So we can kind of override the behavior so we can get the true minimum or the true maximum or whatever it is we might be looking for. And actually the printouts on these aren't really that interesting, but let's just see. If you run it, you get the list sorted in reverse order. You get the list shuffled around. You get the minimum and the maximum value. It actually kind of took me a few minutes. I'm looking at this going, I had to remember integers. And you go, well, -8, is it bigger than -20? And you go, oh, yes, it is. On the number line. All right, so hopefully I had to do a double take. It's been a while, actually. I haven't been in a math class in centuries. So I could figure out the minimum and the maximum. That was a no-brainer. So, all right. Questions on the linked list example? In fact, if you go online, you're going to see many, 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 many different implementations of this. What you want to do for the assignment is to focus on the collections.sort. Actually, this is shuffle. Here we go. This is the method that you want to Google if you want more examples that are actually going to make more sense to you. Because that's what you need to do for the particular assignment. Let's take a look at iterators. Last but not least, we have the iterator example. And what do we got? Just a simple old array list. It might make it easy. You can apply an iterator to anything, to a linked list, to a sorted list, to whatever it is. If the logic applies. So you're adding an element to the array list here, C, A, E, B, D, F. Good. And you're going to use the iterator to display the original contents. So we're going to print out, here's the original contents of the AL, and AL stands for ArrayList. Very unique. Extremely original. Iterator, ITR, is the name of my iterator that I'm making a new instance of. And it's going to be an ArrayList.iterator method that I'm running. And the iterator method is essentially part of the ArrayList library. So while, this is the different part here. Without an iterator, how are you going to have a hasNext or a hasPrevious? There's no way of actually using this functionality. This, you could have, I guess you could have, if this was an array, you'd go, you know, I is equal to 0, I is less than the size of the array. We've seen that already earlier. Go through each one of the elements in the brackets I, index I, all over again. This saves you and it implements it automatically for you. So we have the object element that is equal to the next object. So just as how all those people were employees and they were instructors and they were students, well, they're also objects. Because everybody's inherited from object. Everything in Java is an object. So here we can say object element, not really care what it is. We're storing it, we're using it as a temporary variable to store of a type object, which is going to be our array list objects that we're storing in here. And now we're going to print out the element. And it's just storing a piece of information that's in the list. Because here it's equal to the next item, to the next item, to the next item. So this is actually kind of a concept of using object. You'll see object used a lot. Sometimes with the parameters for method calls. Give me an object. I really don't care what it is. How you can create a polymorphic kind of method is to have the parameter object O. You'll see that, or obj for object. And it just takes, the method just takes an object, so you can send it an integer object. You can send it a float object, as long as it's, you know, an object, which everything is an object. In fact, you can even send it a variable because it's an object. And it causes confusion because people go, well, you know, it's not specific. It's not telling me, you know, it's a string or it's a float or it's a double or whatever. But that's kind of how you can implement a lot of behavior, you know, and send an object. Because you don't, unless you're working with object orientation, you're not really sending objects, passing them as parameters, or returning them from functions or anything. So, so you probably have never seen that. All right, so let's get back to the iterator. I think that's what I was looking at. Yeah, the iterator. So we can print out, so we can modify. So now we have a list iterator. This is just an iterator. It has the basic functionality of going next, 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 or previous, 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 or anything that you've implemented for it. And we can modify the list now. And if we're going to modify the list and print it out, we create a list iterator, which is just a variation of it. Just a variation of an iterator, but it's specifically designed for list manipulation. So we can modify it. So here we have a list iterator, and while hasNext, same as before. All we're doing here is we're just modifying it. So modifying the objects, basically being iterated. So it allows us, it gives us a little bit more functionality. It's a built-on, it's an inherited class from the iterator. You can create your own iterators, actually. Call it my iterator, whatever you want to call it. I wouldn't reinvent the wheel. If you're going to use an iterator, just use an iterator. Or if you're going to use, so, you know, something that's already built in, just use it. And so here we have, what are we doing? We're modifying the contents. We are printing them out. What is this? hasNext, hasNext. Here's a we're going to do it the exact opposite direction. We're going to iterate it backwards. So now we have a hasPrevious object here. So if we print this out, if we run the program and see what the output's going to be, we get a bunch of system outs with our list. So we have the original contents A, B, C, whatever, or A, B, E, whatever. Modified contents, we've added the plus to it, and now we've listed it out backwards. So iterators give us natural built-in functionality to go through a list that's not numeric. That's not. You're iterating objects, and you're applying the iterator. You're creating an iterator, applying it to the object, taking the object and running the function and the methods of the iterator on it, so that you can traverse the list. So it gives us the functionality that we would actually have to implement ourselves if we were creating a linked list like in C++, because we would have to go next, beginning, delete an object. And this is essentially just going through a list. We can add, delete, we've seen the add, we can remove, we can sort, we can shuffle, we can do all sorts of different method calls on the particular object to make it give us the functionality. And I've seen people implement their own list structure. Personally, I don't know why, outside of educational reasons, or they don't know this exists, perhaps, which might be it. I don't know. But these are the examples, and as promised, we're going to take a break for maybe 10 minutes. It's 1:15 already. But these are the examples that are associated with the particular. Now, the assignment's not this easy. The assignment definitely, the second part is doable, I think. The first part with the whatever, map, I can't remember what it's called, is definitely more complicated. But as I mentioned before on that as a side note, if you can't handle it, don't worry about it. Just do come close. And as long as you made a reasonable attempt to complete it, on that particular one, I'm not going to hold you to the functionality. So, questions on collections? Actually, the collections class uses interfaces inside of the implementation. We have an interface for a list that's implemented in a linked list, and an interface for the array list. And those interfaces, can be combined to create all sorts of different types of lists, which is why the presentation of interfaces along with a concept is good. So, okay, let's take a quick break for about 5 minutes or so. We'll come back and then we'll do swing.